So we're in chapter 6, and we want to start looking at normal distributions, which are a special type of continuous probability distribution. So the goal is to transition into continuous probability distributions. Remember the distinction between continuous and discrete. When you're talking about discrete, you're talking about counting numbers only. But as soon as you start talking about continuous, you talk about decimals, and there are infinitely many decimals. So we were looking at discrete probability distributions. Remember that in chapter 5, right? Discrete. So remember what a discrete probability distribution entailed. You had a random variable that took on counting values. So discrete here refers to you're taking on counting values for your x. So your variable x is discrete. So for example, remember what a random variable is. It's some quantity whose outcomes are determined by chance. So if I'm talking about x being the number of boys you will have if you were to have 3 kids. So let's say you have 3 kids. How many boys could you have? You could have 0 boys, 1 boy, 2 boys, or 3 boys, right? If you were to have 3 kids. So that's something you can count. 0, 1, 2, or 3. And that's going to be determined by chance if you're having a boy or a girl, right? And what are the probabilities? Well, probabilities always go from 0 to 1, and they have to tally all the way up to 1. All the probabilities have to tally up to 1, right? So let's say we have for 0 boys 0.125 chance, for 1 boy 0.375, for 2 boys 0.375, and for 3 boys, all of them being boys, 0.125. Right. The probabilities go from 0 to 1, and all the probabilities tally up to 1. So this forms a probability distribution. It's discrete because the x values are counting values. So I mean, you can make it into a table. You can always make a discrete probability distribution into a table, or you can make them into a nice little graph here. You put the p of x's on the vertical axis and the x's on the horizontal axis, going from 0, 1, 2, 3. Here we go, 0.1, 0.2, 0.3, 0.4, let's say, and just plot these discretely, right? Discretely meaning going 1 by 1 by 1 by 1. You got these individual points here with the bars, or the sticks. So you can make a discrete probability distribution into a table or to a stick graph with the little points on the end. But what happens as soon as you start dealing with continuous data? So let's say your x, whatever x represents, maybe it represents weights. Let's say you're randomly selecting someone and you're talking about weights. Well, weights can take on decimals, right? So I could have someone who's like 165 pounds, or someone who's 165.1 pounds, or 165.11, or 165.111. Do you see a problem? We can never write out all the decimals, right? It's impossible to write out all the decimals. There are infinitely many decimals that could be written. We could have someone who's 165.132.897. So you'll never be able to write out an entire column of x's. So we don't even try to make a table when we're dealing with continuous data. Continuous data. So we're not even going to bother making a table as soon as we get continuous data. That's not the way to go. So you have a continuous probability distribution when your random variable x takes on decimal values. Also, probabilities are going to go from 0 to 1. Probabilities that are always greater than or equal to 0, always less than or equal to 1. But rather than tallying up probabilities, what we're going to do, we're going to represent the distribution as an equation. And we're going to call this equation a PDF, or a probability density function. So you can write an equation, call it f of x. There's going to be some equation, you call it f of x. And what you can do, you can graph this function on a x-axis and a vertical axis. And who knows what it'll graph like? Maybe it'll graph something like this, Maybe it'll graph like that. And when you calculate the area under the entire function, calculate this area here, that area is going to tally up to 1. That entire area tallies up to 1. So the area under this curve here is going to be totaled up to 1. Now, how do you actually calculate probabilities? How do you calculate probabilities? Well, what you're going to do, let's say you wanted to find the probability that an x value is, I don't know, between 2 and 3. What you would do, you'd find, okay, 2 right here, let's say 3 right here, and you find that little area under the curve. So probabilities are going to be areas underneath the curve along intervals. In this case, you're talking about the interval from 2 to 3. So that's the way you find probabilities when you have continuous distributions. Okay, so here's some very famous continuous distributions. Just give you a clue about this. The first one we're going to call the uniform. The uniform, you really don't need to know this, but the uniform, the graph looks something like this. That's called your density function. The second one we're going to call the exponential. It starts up high and it dips down and gets close to 0. It's called the exponential. The gamma has different forms depending on your quantities involved, but generally it kind of starts down low, goes up high, and then dips down again. And then the most famous distribution, this is the one we're going to focus in on, the one called the normal. The normal. And the normal has a certain probability density function, which I've written the equation here. F of x equals 1 over sigma times square root of 2 pi times e to the negative 1/2 x minus mu over sigma quantity squared. So first of all, the mu here, that blue thing, that's called the mean. That's going to be a number. And the sigma, that's called the standard deviation. It's going to be a number. And it turns out that when you graph this function, graph this equation in 2 dimensions, the mean is going to be at the center. The mean is at the center. And the curve of this probability density function is kind of bell-shaped, right? It's shaped like a bell. It's symmetric about mu. What do I mean symmetric? I mean to the right of mu has the same kind of shape as what's to the left of mu. So the mean is mu, the standard deviation is sigma. It's bell-shaped and it's symmetric about the mean. That's what's called a normal distribution. Now, if you look at some restricting things, if you make the mu 0, if you set the mu equal to 0, and the standard deviation equal to 1, you get what's called the standard normal distribution. And that's what we want to start in this section. We want to start looking at what's called the standard normal distribution. The standard normal distribution is also called the z distribution, and it's basically just the normal distribution with mean 0 and standard deviation is 1. So just keep that in mind. What is the mean? So here's a question. Maybe I'll put this on an exam or something. What is the mean of the z distribution? What is the mean of the z distribution? The mean is 0. What is the standard deviation of the z distribution? The mean of the z distribution was 0. The standard deviation is 1. Standard deviation is 1, so 2 big facts. Now here's the PDF, if anyone's curious about the probability density function. This is the way we write it. We use z. Rather than using x, we just use z to specially designate the standard normal distribution, and it looks like a normal distribution that's centered about the mean, but this time is the mean 0. So we're actually centered at 0. So you got, okay, z-scores along this horizontal axis. So here you'd have a z-score of 1, z-score of 2, z-score of 3, z-score of 4, and so on. And on the opposite side of 0, you'd have a z-score of -1, -2, -3, and so on and so forth, -4. So 0 is right at the center. You got the positive z-scores to the right of 0, the negative z-scores to the left of 0. So very important. All right, so I guess the next big task is to